For a long time, I wanted to write a paper about David Hume and mathematics because I was interested in the fact that in his first big book, his Treatise of Human Nature, of 1739, having set out his empiricist project and set up his imagist philosophical psychology, what does he do? None of the things that he's famous for, thinking about causality and induction and so on. No, the first thing he does is start banging on about the divisibility of space and the infinite divisibility of extensive magnitudes and how we can't imagine them and therefore all such talk is nonsense. And that is consistent, that is an application of his machinery, but why did he go there first and what, So I set about it and I did what philosophers normally do when faced with a historical text. I did a close reading of his arguments and tried to understand them as arguments. The results weren't that great, they weren't that novel, and were quite properly rejected by journals of note. But on the way to reaching that point, I did some research. I followed up his historical sources, the discussions of mathematics that he mentions. I noticed that they were all from the previous century, that he wasn't exactly up to date in his mathematical references. But I also noticed something else. And what I noticed helped me to realise that my real question wasn't anything about the detail of Hume's arguments about extension. My real question was, David, what were you thinking? You don't know anything about mathematics. I mean, not really. What possessed you to imagine that you were going to resolve questions that had been left unresolved by Leibniz and Newton, to name but two? That was my question. And I got interested because I realised that there is a kind of non-expert, extra mathematical discourse in which mathematics features. That since antiquity, people have been making philosophical use of mathematical paradoxes, originally for skeptical purposes, but that changes when we get into early modern Europe. And this was what Hume was latching onto. This is what Hume was tapping into, and this is what informed him. And part of the clue for this is that the two paradoxical cases he mentions. So if we flip forward from the treatise to his inquiries into human nature of 1748, much shorter book without the disastrous discussion of extended magnitude, in the last section on skepticism, just before he makes his great rousing call for book burning, he talks about the paradoxes of mathematics and how these can give rise to certain forms of skepticism. And the two things he talks about are the constitution of the continuum and the angle of contact, right? So part of the project here is to look back through the history of philosophical use of both the continuum and the angle of contact. And you realise that they come as a pair, as a kind of loosely associated pair. They're like a meme. And part of the argument for that is that there are other paradoxes that could have worked just as well. So, for example, Torricelli's Horn of Plenty, right? Deeply paradoxical, never gets a mention. Why not? It didn't make its way out of the discourse of elite expert mathematicians and into the discourse of generalist philosophers and Salonists and members of the gentry were interested in these questions. So I'm going to talk about the sort of early modern presence in these kinds of texts. So I'm going to talk about the Port Royal logic, where these two puzzles appear as not exactly as a pair. They aren't on the same page, but they're the two cases that you find in there. I'm going to talk about a mathematics textbook called The Elements of Geometry by one Nicolas de Malezieux. And that's interesting because it's a deeply inexpert text. It's not a text written, well, it was written by an expert mathematician, but it wasn't written for expert mathematicians. It was written as a textbook for, well, originally for royal youth, so not for the intellectual elite. I'm going to talk a bit about Leibniz, but not a lot, because I'm really interested in the people who weren't elite mathematicians, so that rather pushes us away from Leibniz. And eventually I'll talk about Hume. Okay, so first of all, quick reminder of these puzzles, paradoxes if you like, as they appeared in the literature. So the first one is the infinite divisibility of matter. I mean, the way this appears in the Port Royal logic and elsewhere is to say that, well, it's been known from antiquity that the diagonal of a square is incommensurable with the sides. And that means that space must be infinitely divisible, because if it were not, if there was some limit scale, some minimal scale in the division of space, some minimal granularity, kind of like the Planck length, that would serve as a common measure between the sides and the diagonal of the square, but that's impossible. We've got a theorem that tells us that. So space must be made up of points that are extensionless, because if they had any extension, they would serve as a common measure, which can't happen. But it's impossible to imagine, form a mental image of how extensionless bits can go together to constitute an extended magnitude. I mean, this is a serious and familiar problem, and leads to a fair amount of mathematics. As you get through the 17th century and into Hume's time, this becomes the problem of the logical foundations of the calculus, which Hume rather runs together. The other case is less familiar. The other case is the angle of contact. Specifically, the angle of contact between a circle and a tangent, a straight line that touches it tangentially. Now you may say, there is no angle there. What are you talking about? Where's the paradox? And of course you're right. But this just shows us why we should not be Whiggish in our history of mathematics, right? That the angle of contact is a nice example of why we shouldn't only study successes and breakthroughs. We should also study mistakes and errors and failures, because they also tell us something important about the history of mathematics and related human endeavour. And the reason the angle of contact is a thing is because Euclid said this. So the crucial bit there is the bit at the end, where he says that the angle of the semicircle is greater and the remaining angle less than any acute rectilineal angle. So that makes it sound like the angle between the circle and its tangent is a magnitude, and what's more, is homogeneous with the angles formed by straight lines, right? So you can compare them in magnitude. So Euclid says this. Euclid tells us that there is such a thing of an angle as an angle of contact, And what's more, you can compare its size with rectilinear angles, or angles properly understood. And this causes all sorts of trouble. This conflicts with the Archimedean principle, because given two homogeneous magnitudes, you should be able to reduce the larger one by cutting it in two bits and always choosing the smaller one until you get a bit that's smaller than the smaller of the two magnitudes you started with. But that's not going to work in the case of a rectilinear angle and the angle of contact. And the case that the version of this that bothered Leibniz is that it seems to counteract the principle that the whole is greater than the part, right? Which was tremendously important to Leibniz. So a point I want to make about this is that this is only a thing because of the authority of Euclid, right? Were it not for the authority of Euclid, if anybody else had suggested that there is such a thing as the angle of contact, you could have easily dismissed it. But because Euclid says it, it's taken seriously and it's discussed. Who discusses it? Well, there are various discussions through the Middle Ages. In the 16th century, it was the object of a dispute between Christophe Clavius and Jacques Pelletier-du Mont. They had a general quarrel of the ancients and moderns. Pelletier was, saying, well, look, there's no angle here. Euclid just misspoke. Clavius insists that Euclid is basically fine, and that if there seems to be a problem in Euclid, then it must be the way we're reading him. They also disagreed about superposition, the legitimacy of superposition as an inferential procedure. So one of the things that's going on here is that because the angle of contact is only a thing because of the authority of Euclid, the history of the angle of contact draws you out into the larger question of the reception of Euclid and what people take Euclid to be. I mean, traditionally and canonically, the model of rational thought and organised scientific human knowledge. But of course, the experts knew that there were some logical difficulties. And so one of the interesting things is that you get this in the early modern Europe, you get this plethora of editions of Euclid. Why should you buy my edition of Euclid rather than somebody else's? Well, because in my edition, I've made some interesting and subtle changes to fix some of the problems and make it easy to read. Maybe I've rewritten some of the axioms, or added new axioms or something, right? So there's a great burst of revisionary Euclid publication around this time, and that tells you something that Euclid is still canonical, but the authority is starting to slip. People are treating Euclid in a way that they wouldn't treat Holy Writ. So Clavius and Pelletier have this debate. Galileo mentions the angle of contact as one of three problems that give rise to skepticism. Leibniz picks it up from Galileo. Leibniz's concern is to resist skepticism. It's mentioned, as I said, in the Port Royal Logic. John Wallis lectured on it in the 1650s, as he was required to do by the terms of his professorship. Interestingly, it was that important that it was written into the bequest that whoever had the civilian professorship would lecture on this topic. It inspired Hobbes's invective. So by Hume's day, the angle of contact was well known to non-mathematicians as a source of paradox and difficulty, and but amongst mathematicians, it had fallen into disuse. That Wallis thought he'd fixed it. Leibniz, as we'll see, decided that Pelletier was basically right, that there is no angle there, that Euclid just misspoke. And that's more or less where the mathematicians are by the time Hume gets going. Hume doesn't know this, right? So he's writing as if he were still in the 17th century, as if it was still a hot topic and an embarrassment for mathematics. So the Port Royal Logic, first published in 1662, went on to be arguably the most influential logic textbook from its date of publication to well into the 19th century. It says here that there were at least 63 French editions and 10 English editions, and that it featured in the syllabus, the logic syllabus in Oxford and Cambridge. So, very influential book, which is kind of curious considering that it's, Antoine and Nicole was so heavily involved in religious disputes in France at their time. They were Jansenists, and it's associated with Jansenist scholarship. And reading it now, you find yourself reminded of that context in every page, because they again and again they they connect issues in logic and semantics and epistemology and philosophy of science with religious disputes, as we will see. Nevertheless, so in spite of that very French, very Catholic, very religious state of affairs, origins, context, it explodes and becomes, a central logic textbook. Possibly because it's very easy to read. It isn't massively technically demanding. There are 4 parts. In the 4th part, first section, they discuss geometry. Now I'll read chunks out of it to you. So they make the argument that I made earlier, that from the incommensurability of this diagonal on the square, that space must be infinitely divisible, but we can't understand this. They make another argument about infinite divisibility, which I haven't seen elsewhere, and which Hume doesn't discuss, which is that they make this conditional argument that, well, you can understand infinitely large magnitudes. Just imagine an infinitely vast ocean, level, plain ocean. And if you can understand that, which you can, then you can understand infinitely small magnitudes. Because if you imagine a ship sailing away, and you're looking at this ship through a telescope, then the apparent height of the ship will get smaller as it recedes. And if you're doing this on an infinitely vast horizontal ocean, the ship can go as far away as you like, and so the apparent size can get as small as you like. And you can take away the subjectivity of the apparent size by thinking about you're looking at it through a telescope, and think about the points on the telescope lens where the light rays corresponding to the highest and lowest parts of the ship intersect with it. Well, those 2 points on the lens can be made as close as you like by having the ship sail away as far as you like, right? So if you can understand infinitely large magnitudes, then you are stuck with, by that argument of, given a triangle with a fixed height, you can extend the base as far as you like, and then the height, a fixed distance from the acute angle, will get as small as you like. So that's the kind of argument they make. And what do they say about it? They say the following: the benefit we can derive from these speculations is not just to acquire this kind of knowledge, but to teach us to recognise the limits of the mind, and to make us admit, in spite of ourselves, that some things exist even though we cannot understand them. This is why it is good to tire the mind on these subtleties, in order to master its presumption, and to take away its audacity, ever to oppose our feeble insight to the truths presented by the Church, under the pretext that we cannot understand them. And so on and so forth, more in the same vein. So the point of this is fideism. The point is there are some things that we know to be true, but which we can't understand because they seem to be in contradiction with other things which we also think we know to be true. What do we have to do? We just have to believe. A bit later in the same discussion, they mention the angle of contact. And all they say is this. They say, some geometers contest verbal definitions as heatedly as if it were a question of the things themselves. Thus we can see in Clavius's commentaries on Euclid a long and quite heated debate between Pelletier and himself concerning the space between the tangent and the circumference, which Pelletier claimed was not an angle, whereas Clavius maintained that it was. But who cannot see that all this could be ended in a word by asking each of them what he means by the word angle? So, two observations about this. One is that they don't feel any obligation to expand upon the argument and to explain in any detail what the mathematics of this is all about. So they take it that their readers already know about this angle of contact dispute between Clavius and Pelletier. And remember that their readers are not the mathematical elite. Their readers are the philosophically interested gentry, the informed general reader, right? So they assume that everybody already knows about this dispute, which tells us something about the currency of the angle of contact in those circles at the time. The other thing is that they think it's just verbal, right? That if Clavius and Pelletier just defined their terms more precisely, they would see that there's no issue between them. But of course, there's much more to it than that. Because the terms are used in an argument about infinitesimal scales, all of the arguments about the angle of contact are all about, well, what happens if you make the circumference bigger and bigger and bigger? You know. So they're all versions of kind of like exhaustion arguments. So this is absolutely at the core of the technical disputes, technical problems that mathematics had at that time. They can't just fix it with a word and agree to differ. There's far more at stake than that. And Antoine and Nicole don't seem to realise that, which suggests to me that they're writing with a relatively low level of mathematical expertise. Okay, that's as much as I want to say about the Port Royal logic. I want to say a quick word about Leibniz, but I won't say much because he's very well studied, not least in an excellent paper by De Lasso. The interesting thing about Leibniz is that he operates on two levels at once, and he says different things on the different levels. He inherits the angle of contact problem from Galileo. It's one of three problems that he thinks give comfort to skeptics. So that's what he's against. He wants to make sure that skeptics don't have arguments to bring against human reason. So he's in a different game from the Port Royal logic, right? So Arnaud and Nicole want to say, there are limits to human reason and we need to know where they are, and mathematics can show them to us. They also say, interestingly, Arnaud and Nicole, they say that inevitably the mind is dissatisfied with knowing that something's true without knowing why. So right there, you put that together with their claim that there are some things we can know to be true but can't understand why. Right there you have the tragedy of human reason that reappears in Kant. The idea that reason is inevitably led on by its own nature. It's a tragic hero in this case, in this sense, right? Its very nature leads it to its own destruction. Right? Human reason is led by its own nature to ask questions that are unanswerable. Leibniz, both as a matter of doctrine and as a matter of character, isn't really into the humility of human reason, right? Leibniz thought we can know stuff, we can know things absolutely, and that's very important. It's very important that we can know things from first principles, and so carrying the fight against skepticism was important to him, and this is why he gets interested in the angle of contact. As I've already mentioned, when he's thinking as a mathematician, amongst other elite mathematicians, his answer is to say with Pelletier that there's no issue here. Euclid just misspoke. The interesting thing is that in Letters to Royalty, he does something different. In Letters to Royalty, he uses the angle of contact to make theological analogies. So, there can be a nature which is infinitely superior to all other natures, right? Just as there can be an angle that's infinitely smaller than all other angles, but is nevertheless an angle, stuff like that, right? So he makes, at the same time, when he's thinking like a member of the mathematical elite, he dismisses the angle of contact as a non-problem, but that doesn't prevent him, when he's participating as an honoured and distinguished guest in the discourse of non-experts. So when he emerges from the society of elite mathematicians and enters the salon of keen amateurs, there he deploys the angle of contact as an analogy that you can use for theological edification. He was a courtier. Moving on, I want to talk now about a book that you may not have heard of, and that is The Elements of Geometry by the Duke of Burgundy, with a bit of help from Monsieur de Malezieux. So this was a mathematics textbook that came out in the early 1700s, first in French, then there was a Latin translation, and then later there was another French edition. Now, this is kind of fascinating. So Malezieux was a mathematics tutor to the teenage Duke of Burgundy, who was also the Dauphin, right? So the French crown prince, the crown prince, never ascended to the throne because he died of a fever as a young adult, and Louis XIV outlived him and everybody else, and so the crown skipped a generation. So the story is that Malezieux is giving these maths lessons to the Dauphin, and the Dauphin is taking notes. And do you know, these notes were so perfect, they were so clear, that they just had to be bound and published. So this is the legend. This is the royal connection that makes this maths textbook sell in a way that it probably wouldn't have done. So you see that the first edition is presented as by the Duke of Burgundy, and then later editions, the later French edition, after the death of the Duke of Burgundy, Malezieux's name appears on the title page. There's a long dedication which talks, amongst other things, about the usefulness of mathematics for all sorts of practical purposes, including the art of war. And this is a reason why royal and aristocratic youth ought to study it. The irony is that the Duke of Burgundy was useless at the art of war. He was allowed to conduct a campaign. He was hopeless. Didn't follow the advice of his field officers, insisted on waiting for advice from Paris. As a result, battles were lost and towns ceded to enemy powers and so on. What was in this book? Well, it's mostly basic algebraic geometry, the stuff which, had it been published 70 years earlier, would have been very current. It's basically what you find in sort of mid 17th century summaries of Cartesian algebraic geometry. But you also find these little philosophical breaks. So this is why we're interested in it, that in the midst of this rather basic mathematics textbook, which is, suitable for a not particularly brilliant royal teenager, you find these quick outbursts of philosophy. And what do you find? You find precisely the arguments that were there in the Port Royal logic, somewhat elaborated, but basically there's the diagonal argument. The diagonal on the square is incommensurable with the side, and therefore space must be infinitely divisible. You find the angle of contact argument, but elaborated in a way that I haven't seen elsewhere. You're invited to imagine a globe or a sphere sitting on a plane, and then you're invited to imagine what goes on with the angle between the globe and the plane as the globe is increased in size. It doesn't change the argument, but I don't know, doing it in 3 dimensions somehow, I suppose, must make it more vivid. There's a third argument that Malesherbes introduces, where he says that unities must be composed of other unities, right? So he presents that as the reason why this is a paradox, right? So you've got a dialectical twin. On the one hand, you've got a pair of arguments, the angle of contact and the Pythagorean argument, to show that space must be infinitely divisible. And then you've got this other argument to say, well, any unity must be composed of other unities. That, in other words, it's a version of the argument that you can't make a continuum out of extensionless bits, extensionless points. And it's that dialectical pair that creates the skeptical moment and allows Malesherbes to make the same conclusion that we found in the Port Royal logic. So, why am I telling you about this? Well, only because, sure, it's the Port Royal logic argument round again. There's not a lot of novelty there. What's new is how very far it's got from the mathematical elite. Because although Arnaud and Nicole are not mathematicians, and I think what they have to say about the angle of contact reveals that, nevertheless, they are part of the intellectual elite generally, right? They are amongst the writers and disputants of their time. Whereas, this book by Malesherbes, and I think we should take it that it is by Malesherbes, we don't need to take seriously the legend about the Duke of Burgundy being the author. It's just a basic maths textbook aimed at anybody, any teenager or any, aristocratic or royal person who wants to know the kind of basic mathematics of the time. So although it's associated with the social elite, it's well away from the intellectual elite. And yet, there we find these two arguments together, these two puzzles together, the angle of contact and the constitution of the continuum, in the specific shape of that argument about the diagonal and the side of the square. So why do I know about Malesherbes? Well, because Hume mentions him. Hume, in the treatise, is sort of looking around for arguments against the infinite divisibility of magnitudes, extended magnitudes, and he, from somewhere, he's got Malesherbes' argument about unities must be composed of smaller unities. Hume doesn't present it as part of a dialectical pair because he doesn't want the skeptical conclusion. He just wants to show that space cannot be infinitely divisible. So he doesn't show the whole of Malesherbes' dialectical structure. He just reproduces the side of the dialectical pair that argues that space cannot be infinitely divisible. It's not known whether Hume read Malesherbes' argument in Malesherbes' book because some bits of Malesherbes' book were reproduced in journals, right? Presumably the philosophical bits, because there'd be no point in republishing the maths, because the maths was basic stuff from 50, 60, 70 years earlier. Of interest for us is not so much what goes on in the treatise, but what Hume does in the inquiry. So here we are, 1748, long after everybody else I've been talking about is dead. Nobody else is talking about the angle of contact. And the discussion about the composition of the continuum has moved on some way, but Hume doesn't seem to know anything about that. There are some authors who try to argue that, oh, well, maybe Hume knew about the mathematics of his day because some of it was being written, at the University of Edinburgh while Hume was a student there. But the mere fact that there were leading Newtonians writing Newtonian treatises about the fundamentals of calculus while Hume happened to be in the same town doesn't prove anything. There's no record of exactly what Hume studied, and nothing in his writings suggests to me that he really understood what was happening in the mathematics of his time. In fact, if anything, the reverse. So what does he say? He's talking about space and time, the abstract ideas of space and time. And he says, no priestly dogmas invented on purpose to tame and subdue the rebellious reason of mankind ever shocked common sense more than the doctrine of the infinite divisibility of extension, with its consequences, as they are pompously displayed by all geometricians and metaphysicians with a kind of triumphant exultation, right? A bit like Berkeley. Berkeley talks about, how pleased the scientists and mathematicians are with calculus, and yet when we examine its fundamentals, what do we find? We find confusion and contradiction, right? That was Berkeley. So Hume's on a similar jag. A real quantity, infinitely less than any finite quantity, containing quantities infinitely less than itself, and so on in infinitum. This is an edifice so bold and prodigious that it is too weighty for any pretended demonstration to support, because it shocks the clearest and most natural principles of human reason. But what renders the matter more extraordinary, he says, is that these seemingly absurd opinions are supported by a chain of reasoning the clearest and most natural. Nor is it possible for us to allow the premises without admitting the consequences. So that's where mathematics lands us. It leads to absurdities. It leads to this absurd picture of infinitesimals within infinitesimals. But the reasoning that gets you there seems to be inescapable. Nothing can be more convincing and satisfactory. Okay, so now we're moving on from the first of the two standard items that always go together, the constitution of the continuum, And we're moving on to the second one, the angle of contact, right? So, nothing can be more convincing and satisfactory than all the conclusions concerning the properties of circles and triangles, and yet, when these are once received, how can we deny that the angle of contact, hooray, between a circle and its tangent is infinitely less than any rectilinear angle, and that as you may increase the diameter of the circle in infinitum, this angle of contact becomes still less, even in infinitum, and that the angle of contact between other curves and other tangents may be infinitely less than those between any circle and its tangent, and so on in infinitum. The demonstration of these principles seems as unexceptionable as that which proves the three angles of a triangle to be equal to two right ones. Also, the absolutely standard go-to example of a theorem, right? The inner angle theorem. It's there in Aristotle, and whenever anybody needs an example of a reliable, easily proved geometrical theorem, that's the one that you go for. Yes, so the demonstration of the results about the angle of contact is as easy and obvious as the demonstration of the inner angle theorem. Reason here seems to be thrown into a kind of amazement and suspense, which, without the suggestions of any sceptic, give her a diffidence of herself and the ground on which she treads. She sees a full light which illuminates certain places, but that light borders upon the most profound darkness. And between these she is so dazzled and confounded that she scarcely can pronounce with certainty and assurance concerning any one subject. So he goes on. But the way he gets out of this is to say that, but you can't stay there. That the kind of skepticism that you end up with, where you don't, where reason doesn't believe any of its own reasonings, because it's reasoned its way into paradox, is itself unsustainable, and then you wind back, and you end up with a kind of common sense. But then there's a footnote, which I think reveals to me that Hume, like Arnaud and Nicole, just didn't understand what was at stake, because when he's talking about the constitution of the continuum, he adds a footnote. Well, it says, if they just realised that there are no such thing really as abstract ideas, that when we think we have an abstract idea, what we have is a mental image of a particular, and we use that to reason about generalities. If these mathematicians just understood that point of mine, then all of this stuff about the infinitely small or the infinitely big would go away. But of course, mathematicians needed to found the calculus. They needed a logical basis for the calculus, because that's where the hot mathematics was. And just to say on empiricist grounds, actually, it's not possible for humans to reason about infinitesimal matters, doesn't give them what they need. So Hume, I think, didn't really understand what was at stake in all this, and he writes about the constitution of the continuum and the angle of contact as two examples of paradoxes that throw human reason into kind of a state of brief, temporary state of skeptical confusion, indifferently, right? He doesn't seem to have noticed that, or doesn't seem to know that one of them, the angle of contact, has just ceased to be a problem for serious mathematicians, whereas the other, the constitution of the continuum, is the serious problem for mathematics, and would remain so for the next few centuries, and arguably into our own time. So the conclusion here is that we've got two levels of discourse. We've got the discourse of elite mathematicians like Leibniz and Wallis and Barrow, all of whom discussed both of these cases, the angle of contact and the constitution of the continuum. And then you've got people like Arnaud and Nicole and Malesherbes, and presumably the Duke of Burgundy and the people who bought that book, the people who bought and read and used and were examined on the Port Royal Logic, and Hume, for whom these two bits of mathematics are puzzles. And you can either use them to conclude that human reason has limits, and they show us the limits of the human reason, and the point at which faith should take over, and so you get the Fides conclusion. Or you can use them to continue the skeptical tradition that you get, just as you have Sextus Empiricus using xenoparadoxes for skeptical arguments. So you get people like Bale discussing that kind of argument. And that's what Hume is commentating on. So the reason that Hume thought that the constitution of the continuum and the infinite divisibility of space and time was within his intellectual scope was that there was a long tradition of non-experts, non-mathematicians talking about, writing about, having opinions about those topics, and that discourse had kind of got detached from the discourse of expert mathematicians. And you can see that in Leibniz, that Leibniz doesn't feel any compunction about operating on those two levels at the same time, because they're separate. And you can also see the separation of those two levels of discourse in the fact that Hume is still engaging in the non-expert discourse as if he's still partying like it's 1699 into the 1740s. That's the story. Hume thought he was entitled to write about this stuff because there was a whole tradition of non-mathematicians who thought that they were entitled and competent to write about this stuff. And he was wrong. And present-day philosophers ought to think about that.